Now we start a new topic, RC circuits. This is example number 1. Certain capacitor initially uncharged is connected in series with a resistor and a battery. So let me draw it for you. So we have a battery, okay, a resistor, and this is our capacitor initially uncharged. So this is R, this is E, this is my capacitor, capacitor C. After being charged for 10 milliseconds, the charge on the capacitor is half of its maximum value. So we have to apply the formula for charging capacitor. You have to read the problem carefully because sometimes the capacitor is uncharged and we charge it, and in other problems we start with the capacitor fully charged, then we discharge the capacitor. And there are different formulas to be used. So charging the capacitor, we know that Q at any time is equal to the maximum charge, which is CE, okay, multiplied by 1 minus e to the minus t over R over RC. Okay, the time constant of the circuit, meaning that he's asking about this RC, this amount which is RC. This is what we call time constant. We want to know how much is this time constant. It has the symbol tau, and it is equal to RC. Tau equals RC, and it is given in units of second. It has the same unit as the time. And this much CE, this is Q max. This is the maximum charge the capacitor can have. Okay, so let us start answering. Because when we reach time t equals 10 milliseconds, the charge on the capacitor, this charge will be half the maximum charge. We want to know how much is the tau or RC of the circuit. So at t equals 10 millisecond, we have Q equals half Q max. Okay, so we'll plug this information in this formula. So we have half Q max equals Q max multiplied by 1 minus e to the minus t. T is given, which is 10 times 10 to the minus 3 divided by RC. We are done. Now we can solve for RC. So Q max will cancel with that Q max, and we can have this 1/2, and this one will go to the other side, so this will be minus 1 equals minus e to the minus 10 to the minus 2 divided by RC. So here we'll have 1/2 minus 1/2, so this will be minus 1/2 equals minus e to the minus 10 to the minus 2 over RC. So this minus will cancel with the minus. Take ln of the two sides. So ln 1/2 equals ln e to the minus 10 to the minus 2 divided by RC. So ln 1/2 is minus ln 2. Okay, and ln e to the minus, this will give us minus 10 to the minus 2 divided by RC. Again, this minus will cancel with that minus. Okay, and we are left with the following. We can write that RC equals 10 to the minus 2 divided by ln 2. Okay, so this is ln 2, and from here we can answer our problem. Time constant, which is tau, equals RC, and this will be 10 to the minus 2 divided by ln 2. If you do this calculation, you will get the time to be 0.0144 second, or simply you can write it as 14.4 millisecond. I think Just reading the problem carefully and choosing the proper formula, and it is a matter of algebra afterwards. Thank you. This is the second example on RC circuit, an EMF source with E of 100 volts, a resistor with resistance 90 ohms, and a capacitor with capacitance 5 microfarad are connected in series. So the situation is like this. We have a battery, okay, resistance, and a capacitor. Okay, so this is E, that is R, and this is C. As the capacitor charges, so it was uncharged, and now we are in the charging process, charging the capacitor. This is a key word. You have to be careful when you read the problem. So it is a charging. What is the charge on the capacitor when the current in the resistor is 0.8? So find Q equals what when the current equals 0.8 amperes. Okay? So let us start with the formula for the current for a charging capacitor. So I, we know that I equals E over R multiplied by E to the minus T over RC. Okay? So we know the current, we know E, we know R, okay, and C. So we can find the time from our knowledge of the current. Okay? And that time we will take it and plug it for the formula for the charge in order to get how much is the charge on the capacitor at that moment. So this is our strategy to answer this problem. Okay? So here we will have I multiplied by R divided by E. All of this is equal to E to the minus T over R over RC. Okay? We'll take ln of both sides, so we'll end up with ln of IR divided by E. Okay? Equals ln of this will be minus T over RC, or the time can be written as minus ln minus RC multiplied by ln of IR over E. Okay, this ln will give us a minus sign. Minus with minus will get the time in positive. If you plug in the numbers, let me plug in the numbers here for you. It will be minus R, which is 90, multiplied by C, which is 5 microfarad. So this is 5, 10 to the minus 6, multiplied by ln of the current, which is 0.8 multiplied by 90 divided by 100, which is E. E is given to be 100 volts. As you can see, this ln will give us minus sign. With that minus sign, you will end up with the time which is positive, and it is equal to 1.485 times 10 to the minus 4 second. This is the time. Okay? We want to know how much is the charge at that time. Okay? So we'll use the formula for charging the capacitor. Okay? Charging the capacitor again, and we will use the formula for the charge. Charge at any time equals CE 1 minus E to the minus T over RC. Everything is there. Okay, just to plug in the numbers. So this will be equal to C, which is 5 micro coulomb, 10 to the minus 6, E, which is 100, multiplied by 1 minus E to the minus T. Time, we have found it to be 1.4, so this is the minus sign here, 1.485, 10 to the minus 4, divided by the RC. R is 90, multiplied by C, which is 5 micro, 10 to the minus 6. Okay? So this is my formula. It is very simple. Using your calculator, you will get that the charge at that moment will be equal to 1.4 times 10 to the minus 4 coulomb, or here you can multiply by 100, divide by 100. This can be written as 140 10 to the minus 6 coulomb, or 140 microcoulomb. That's it for this problem. Thank you. This is the example number 3 on RC circuit. In this figure, he gives us the values for R1, R2, R3, C1, which is equal to C2, and E of the battery, which is 24 volts. Assume the circuit is in the steady state. This is a very important keyword here, the steady state, in the steady state. Or sometimes he says that the circuit is connected for a long time. Sometimes this is another keyword which gives you the same meaning, that the circuit has reached the steady state. Long time. After a long time. This will give us the same meaning. What does it mean? It means that both capacitors C1 and C2 are fully charged. Okay? So the meaning here, C1 and C2 are fully charged. This is the meaning of the steady state, or the meaning of the circuit is connected for a long time. Conclusion, that C1 and C2 are fully charged. What do we benefit when we know that C1 and C2 are fully charged? Okay? They are fully charged, meaning that no current. This implies that no current is passing in their branches. The branch containing C1 and the branch containing C2, no current is passing through that branch. No current is passing through the branches containing of C1 and C2. So there is no current passing here, and there is no current passing there. What does it mean? It means we will consider our circuit to be as follows. So this is my EMF. Okay, this is R1. Okay, and that is R2. Okay, and here we have what? We have R3, and that's it. What do you notice? As if the branches of C1 and C2 are not there. Okay? I have erased C1 and C2. Why? Because they are fully charged. So what? No current is passing through here. As if this branch doesn't exist and that branch doesn't exist. Okay? What do you notice here, my son? That we have the EMF connected with R1, R2, R3 in series. Okay? So this can be reduced to the following. We have the battery connected with one resistor, which is R1, 2, 3. R1, R2, R3. Equivalent is R1, 2, 3. And we can find what is I equivalent. And this I equivalent will be passing through the 3 resistors. Okay, so this is I equivalent. It is the same current which will pass through the three resistors. Okay, so how much is that I equivalent? So from here, R1, 2, 3 connected in series. So their equivalent R1, 2, 3 is R1 plus R2 plus R3, which is 5 plus 10 plus 15, which is 30 ohms. This is R1, 2, 3. To find what is I equivalent, if you use the loop rule here, this E, which is 24 volts, okay? So we say that 24 positive, because we go from negative to positive, minus I equivalent multiplied by R1, 2, 3. All of this is equal to 0. So I equivalent will be 24 divided by R1, 2, 3, which is 30 ohms, and I equivalent will turn out to be 0.8 amperes. 0.8 amperes. So this current, 0.8 amperes, is passing through R1, R2, and R3. So what is the power dissipated in resistor R3? Okay, so power dissipated, power in resistor number 3 will be this I3, the current passing through resistor number 3 squared multiplied by R3. But the current passing through I3 is I equivalent, okay? I equivalent squared multiplied by R3, and this will be 0.8 squared multiplied by R3, which is how much? It is 15. And this will give us the power dissipated through resistor number 3, which is 9.6 watts. And this is the answer for example number 3. Thank you. Bismillah ar-Rahman ar-Rahim. This is the last example on RC circuit. In the figure, which looks a little bit complicated, but it is not if you choose the smartest loop. All the capacitors are equivalent and have capacitance of 6 microfarad. And all the batteries are equivalent and they have EMF of 10 volts. What is the charge on capacitor C? This capacitor, which is labeled C, we want to know how much is the charge on that capacitor. So let us assume that this side is negatively charged. Okay, here negative, and there is positive. Okay, and let me remind you for the rules which we covered so far. For resistor, this is the resistor. We need to take care of the direction of the current. If the current is going this way and you move this way, you will experience delta V equals minus IR. Okay? But if you move opposite to the direction of the current, you will have delta V equals plus IR. This is the resistor rule. Okay? For the battery, if we have a battery, the short line represents the negative, that is the positive terminal. If you go from negative to positive, this delta V is plus E. And if you go from positive to negative, delta V will be minus E. Here, potential increase. Here, potential drop. So this is what? This is for the EMF. Okay? Last, for the capacitor. What is the rule for the capacitor? If you have a capacitor, okay, and this is negative, that is positive, we'll treat it similar to the EMF. Okay? If you go through the capacitor from negative to positive, there will be potential increase. The potential increase here is how much? Is Q over C. That is plus Q over C. If you go from positive to negative, delta V will be potential drop minus Q over C. Okay, this is just a quick review of the Kirchhoff voltage rule, and let us apply it here. Now, there should be a smartest way. You remember the example which we had, the complicated maze for the resistors? We'll do the same here. We have to choose a loop, smart way, such that we don't include any capacitor except this capacitor of interest. Okay, so to answer this question, we say the following. Choose a loop avoiding other capacitors. Why? Because each capacitor will have its own charge and it will be very complicated. So many unknowns, and you will not be able to answer the question. Okay? So we will choose a loop with only one capacitor, which is this capacitor of interest. Okay? And others can be EMF, okay, but not capacitors anymore. Okay? So I have proposed this minus and plus. It might be correct, it might be wrong. After finishing the problem, we will know whether this is a correct choice or reversed choice. Okay? So let me start the loop. I'll start from this side to that side. I go this way. I'll avoid passing through capacitors. Okay, so I go here. Okay, there is a way I can go there, here, there. Okay, then what? I can go here, then down like this, here. There is no problem to go through EMF, go there, down. I am done. I am here. And the direction as shown, counterclockwise. Okay, and let me apply the Kirchhoff rule here. I am moving through a capacitor from negative to positive. So this will give me plus Q over C. Okay, here no component until I go through this battery from positive to negative. Okay, so this will be minus E. Okay, and nothing else. I reach. So this will be 0. Okay, so from here we can see that Q over C equals E, or Q equals C multiplied by E. What do you notice? Is it positive or negative? It turns out to be positive, meaning that my original choice was correct. This side of the capacitor is negatively charged. That side of the capacitor is positively charged. That is a correct choice. I know that because Q turned out to be positive. If it turns out to be negative, this will be indicator of opposite sign of my choice. Okay, so this will be C, which is how much? 6 microfarad, 6 times 10 to the minus 6, multiplied by E, which is 10. Okay, so this will be 60, 10 to the minus 6 coulomb, or 60 micro coulomb. And the negative charge is in the left side. The positive charge is in the right side of the capacitor. With this, we finish the chapter. I encourage everybody to read the textbook and also practice as many problems as he can. Problems from end of chapter and also problems from all the exam. With my best wishes. Wassalamu alaikum wa rahmatullahi wa barakatuh.